Hi, everyone. We want to welcome you to this first live session of reviewing the Deep Learning textbook, chapters 1 and 2. Here we're going to cover an introduction to the Deep Learning textbook as well as the Linear Algebra section to kind of give you a better understanding of what it takes to do deep learning. I want to go ahead and introduce ourselves, the people that are currently on the Hangout session, and of course encourage you to introduce yourselves as well in the chat thread so we can get to know each other a little bit better. My name is Laura Montoya. I am new to deep learning and artificial intelligence, just kind of self-studying right now. But I'm happy to be with a really great community. We host meetup groups, in the Bay Area, in San Francisco and Oakland, where we also review other lecture series such as Stanford CS231N on computer vision. And I'll allow the other people on the call to go ahead and introduce themselves as well.
Hello.
Abhishek,
Faizan, go.
Okay. Hello, I'm Faizan Sheikh. I'm from Gurgaon, India. I'm at a job now, doing like a trainee data scientist at Analytics Vidya. Where I work is like my work is like typically building content and creating content for especially related to deep learning and like understanding basics of machine learning and uh, like uh, building a knowledge base for it. I'm interested in deep learning from like my undergraduate degree, and uh, like getting deeper in it is my goal for like the future years. So that's it.
Okay, thanks, Faizan. Hello, everyone. This is Abhishek. I'm currently working for MetaMind as a software engineer, and I did my master's in artificial intelligence from University of Illinois Urbana-Champaign, and since then I have been trying to explore machine learning, specifically deep learning more, and this is one of the initiatives joining Laura in that to achieve that goal. So I look forward to read the whole book with all of you.
Thank you, Abhishek. Yeah, so just a little rundown on how this is kind of going to go. So previously, a meetup group that was reviewing this deep learning book in person in San Francisco, and they would take a chat and just have one person volunteer to kind of do a short presentation on that chapter, but everyone, of course, is expected to read the material on their own and then, ask questions and really have a discussion about the material being covered. That way we all learn collectively and collaboratively, and we're able to gain from each other's knowledge and experience and understanding of the material that's being covered. So this week I volunteered, as well as with my co-host here, to kind of give a good representation of what the material that was covered is, and how you would go about getting started with the mathematics needed to do deep learning and machine learning. And so we prepared, oh, and I do want to say also, we want to make sure that everyone understands that, we're not math professors. Obviously, we're learning just alongside you guys, so there obviously might be things that we don't know. But that's okay. If someone else in the chat thread has an understanding or a better answer for a question that was asked, please chime in. We implore you to take initiative and to help other people out. That's part of the goal of this. And then also, we're just going to kind of go through a broad overview of what was covered. Obviously, the intention is for you to actually read the material yourself, so we're not going to go like a word for word. And then for future sessions, we do ask that other people volunteer to take on the next session. So there is a link on the meetup page where you can sign up to volunteer to cover another chapter in the book. If there's a specific topic that you're most interested in, I would say that would be a great opportunity. Or if there's a time you're just available, that would also be a really great opportunity for you to get your hands dirty and present this material to someone else and kind of help out the group as well. So I did share a link to the slide deck on the meetup page. I think I'm also going to go ahead and do a screen share so I can actually walk through it with you guys, and then and we'll go from there. And of course, so again, this is a discussion, so feel free, co-hosts, to chime in at any point. So let's go ahead and do a screen share. Okay, and you guys can see my screen now, yes?
Yeah, okay.
Yeah, okay, awesome. Okay, great. So yeah, so we're reviewing the deep learning textbook that was put out by MIT. This is chapters 1 and 2, Introduction, oops, sorry about that, and Linear Algebra. So first, the first chapter just gives kind of an introduction to, what is artificial intelligence, what is machine learning, and what is deep learning. Just to give a broader overview, as I say in the book, deep learning draws from concepts which are built upon each other with many layers. This is the knowledge-based approach that utilizes...
Hey, Laura?
Yes.
Yep. Sorry to interrupt. Could you click on your screen, or so that in the stream your screen is visible? Because right now I see my profile picture being visible.
Oh, I'm sorry.
So,
Okay, let's see.
yeah.
1 second. I thought I had the... So, is this? So right now, do you just see your profile picture, or do you see the slide deck?
One second.
Here, let's see. Oh no, you should see the slide deck.
Okay, I'm not sure what others are seeing. I'm seeing my picture still. The slide deck is...
How about you, Faizan? Do you see the slide deck, or do you see your pictures
in the stream.
in the
No,
screen?
I can see Abhishek's picture in the stream.
Yeah, he's also seeing. Okay, now I see slide deck.
Now you see the slide deck. Okay, great. Okay,
Yeah.
so sorry about that little troubleshooting there. So as long as we're on the same page now. So yeah, getting back to the topics that are being covered. So deep learning draws from concepts which are built upon each other with many layers. This is a knowledge-based approach which utilizes logical inference rules. For those that don't know, machine learning is the capability of an AI system to acquire its own knowledge. So this idea obviously has been around for a really long time. And then the performance of these simple machine learning algorithms depends heavily on the representation of the data that they are given, of course. So each piece of the information included in the representation of an object is known as a feature, and this starts building upon what we now understand is machine learning and deep learning. These concepts will get, I think, a little bit more solidified as we go through the rest of the slide deck. Did either of you want to chime in on the broad level overview of what is artificial intelligence, machine learning, or deep learning?
Yeah. So for me, deep learning, like I'm interested in the brain part, like how humans think and make decisions. That's pretty complex to model an artificial system of it. Like I'm interested how deep learning does this. For me,
Yeah.
it's interesting. Yeah.
Okay.
Yeah,
Thanks
that's
for
a great...
sharing, Faizan. So according to my understanding, artificial intelligence is something when we try to impart intelligence in our software systems. The goal is to make them think like humans. And then machine learning is a subset of artificial intelligence in a broad sense. And so artificial intelligence is not just machine learning. It has other techniques also, such as knowledge representation, logical reasoning, game theory. All those are part of artificial intelligence. But machine learning is a subset of artificial intelligence, and then we have certain algorithms which help us achieve the goal where we want to impart intelligence in machines, such as we have recommendation systems. When we log into Amazon, we see the recommended books or the recommended products for us based on our browsing history. Similarly, If you log into SoundCloud, it will recommend you songs based on the other channels or songs that you listen to. All this is all this most of them use machine learning algorithms, and then deep learning is subset of machine learning. Machine learning has many algorithms, and deep learning, it is also known as neural networks. It is a certain type of machine learning algorithm, but it has become there's a lot of scope of research in deep learning because there's so many ways you can architect your neural networks. So it has become a big topic for research in itself. So hence it's kind of become a separate branch.
Awesome. Thank you, Abhishek. That was way more in depth, which is great. Okay, well, let's move on. Now that people have a better understanding of what the umbrella terms for artificial intelligence, machine learning, and deep learning may represent, let's go on to data representation and feature extraction. Artificial intelligence tasks can be solved by designing these right set of features to extract data, for a task and then make predictions. Then providing these features to a simple machine learning algorithm will allow us to, solve a problem or, really find a specific thing that we're looking for. So in this case, when you want to represent the data, you want to try to draw a straight line between two different parts of the data, right? So you have a better view of what you're looking for. So in this case, the Cartesian coordinate system, you can maybe visualize it pretty well, but this would not allow you to actually draw that straight line between the coordinates, right? So to kind of separate out the differences between those data sets. Representation learning allows for better performance over hand design representations such as the Cartesian coordinate. It allows for quick adaptation to new tasks with minimal intervention. And in this way, you can kind of allow the machine to discover features on its own. So the examples that were given in the book included autoencoders, which kind of combines encoders versus decoders of a function. So did you guys want to add anything to maybe what to look for or how better to have or create data representation or feature extraction?
So by data representation and data representation, we mean that we want to let's take an example. Let's say we want to predict the prices of houses in San Francisco. Then we'll collect. Obviously the data that we would go for is the prices of houses in the previous years. Now, how do we want to use? In which format do you want to collect that data? On the algorithm that you're going to use to run to make the prediction of prices, and that format would basically refer to the data representation, and then feature extraction refers to the features, the properties that you're going to use from those that you have got. For example, one bedroom, the number of bedrooms could be one feature, and then uh, the area of the house could be another feature. So all these properties or the factors that kind of that are actually contributing to the price of your house in determining what could be the price of your house. So those things can be considered as features. Yeah, and then we have different representations on the slide. We see Cartesian coordinates, that's the x and y, and in real world not everything cannot be transformed or can be used in the x and y format. So we have polar coordinates where we it's another form of representing the data. It's just that it's similar to x and y, just that we use r, which is the radius, and then theta, and we can there are certain formulas using which we can convert the x and y coordinates to polar coordinates and vice versa. I guess we
Awesome.
can go next.
Thanks, Abhishek. Faizan, did you want to add anything to this portion?
No, go ahead.
No? Okay.
Yeah.
Not a problem. So the next section of the introduction kind of gives us a view of what the deep learning model is. We talked a little bit about how basically it's where you build upon layers of inference rules, right? And over time, the system learns the system learns from those layers, right, that are built upon themselves. So usually you'll have an input layer, as shown here. So in this case, if you're looking at a picture, if you're working with convolutional neural networks, or trying to get a machine learning model to recognize what something is inside of an image, there will be that visible layer, which is the input, and then it'll go through a series of hidden layers, and then the output layer will identify what the object really is. So here it'll basically start breaking down the image into different pieces. So the first layer, for example, will identify edges. So if you're looking at a human face, for example, you'll know that like around the eyes, that would be one edge. It like draws a square box, basically, not really draws, but there's a representation of, these are the features that we look for normally when we're identifying a face, right? So it creates those edges. And then one layer deeper, it starts looking for corners or contours. And then the third layer is those object parts. And then over time, the machine learns that, these are the things that actually make up a human face, or, in other examples given here, a car or an animal. So in this way, this allows for, let's see. Oh yeah, so this allows for the computer to build complex concepts out of simpler concepts, right? So it breaks it down piece by piece, and then can then identify a larger concept over time. Did you guys want to add anything to that in looking at this deep learning model?
I think you covered the most of it. You can go next, unless Faizan have something else to say.
Yeah, go ahead.
Okay, sure. So the next section they kind of cover is the computational graph. So when looking at the machine learning algorithms that are used to actually do deep learning, it's good sometimes to represent it in something like a computational graph, because this will give you a better understanding of what's happening and as it moves through the system, right? So here we have some element sets, and what we're doing is we are trying to either multiply or add these sets of matrices, right? These set of elements within the matrices. So here, let's see. So here we have that depth allows the computer to learn a multi-step computer program, each layer representing the state of the computer's memory after executing another set of instructions happens in parallel. So with the computational graph, this allows for each element set to be represented, right? So for example, for the logistic regression set, there's only one element set, right? Whereas here in, if you're doing the matrix multiplication or addition, you have several element sets or several things that have to occur before you get to your answer, right? So first you have to multiply the elements together and then add them, and then you actually will receive your answer. Does that make sense? Did I explain that correctly?
Yep.
Yep, okay, cool. So from there, it kind of gives a bigger idea of who should read this book. What, who should deep learning apply to? What aspects of artificial intelligence, does this cover? So deep learning is kind of a representation learning, which is then also a kind of machine learning, which is used for many but not all approaches of artificial intelligence. So some examples that were given here for deep learning, the example is multi-layer perceptrons. And those multi-layer perceptrons are just a mathematical function that map some set of input values to output values. So the function is formed by composing many simpler functions, as we kind of already touched on, and then each application of a different mathematical function provides a new representation of the input, right? So that's really what's going to be covered most in this book. Other topics that they brushed over a little bit were autoencoders, representation learning, and then logistic regression, which is pretty standard for machine learning. It's been around for a while. And then, of course, you have a broader idea of knowledge bases. And all of this kind of makes up, what we consider artificial intelligence in this area of artificial intelligence, right? Because it can also be applied to other areas in other industries as well. Do you guys have anything to add on that?
Just one thing, yeah, it's something that I already kind of mentioned. Basically, I guess what they're trying to say here is deep learning is subset of representation learning, which is subset of machine learning, and then machine learning is subset of AI. That's the whole essence of this.
Definitely.
Yeah,
Faizan, did you want to add anything there?
just a small question. Where do you think reinforcement learning lies in this diagram?
So reinforcement learning is another type of machine learning, and so it would lie in the second circle from outside, under the second circle from outside. It will come under machine learning umbrella, basically. And there have been researches where people have combined deep learning architectures and applied deep learning architectures and reinforcement to do reinforcement learning. So those architectures are termed as deep reinforcement learning. And playing Atari games was one of the most one of the recent successful paper where they're trying to teach a robot how to walk and or play games online, make decisions while playing games. It's an interesting paper. I can post the link here.
Thank you, Abhishek. And hopefully you guys are watching that chat thread as well. Because my screen has the slide deck, I can't also look at the chat thread. So please, if anyone has questions or comments that we need to answer, please just shout them out, and we'll go from there. Okay, great. So the next portion that was covered in this section, they wanted to talk about the different parts of the artificial intelligence system and how they relate to each other within different AI disciplines. So in this case, the shaded boxes indicate components that are able to learn from data, right? So here we have the representation learning portion, which falls under, where deep learning falls under representation learning. And so you can see that when you have an input, you start to get simple features extracted, and then additional layers of more abstract features that then have mapping of features, and then you receive your output. And so that follows a similar pattern with classic machine learning. But in that case, you first have those hand-designed features that then create mapping from features and give you your output. So the example of hand-designed features in how I understand it would be, so for example, if you have an image of a cat and you want the computer to identify that this is a cat, you would tell it to look for specific features that are cat-like, right? You can say that a cat, has ears, or it has 4 legs, or it has a tail, and then from there, the machine would look for those features in order to, give you your answer, give you your output, or identify that that is a cat. Did you guys want to add anything to that?
No.
No? Okay, great. Are there any questions in the chat thread?
Yeah, so one question was asked was, can you speak more about why we should focus on deep learning and ML as opposed to other branches of AI?
Yeah. So I don't know if it's really why you should feature on one versus the other. I think from my understanding, it depends on what you're trying to achieve, right? And if your goal is to do parallel processing of, many calculations at one time in order to, find, for example, to predict some value from the data, or, to predict something in the future, that would be a reason you would use deep learning versus standard machine learning. And also, ideally, you would want the system to learn on its own over time, right? You want it to have less input from yourself, right? You don't necessarily want to have to design those features because that takes a lot more time and energy from us individuals if we have to tell the machine what to look for. So if you can feed it enough data, which is now capable, right? Which we have enough data collected, and now we have the processing power available to be able to do those calculations and to do that extraction of features and that mapping on its own, then that would be the reason to do deep learning. But that's not necessary in all cases. Oftentimes, classic machine learning is still very relevant for a lot of industries that are just getting started. Some things that I've read upon recently have been like machine learning being applied to agriculture is really becoming a big thing right now. So, in that case, they don't necessarily need as much computation power, or they don't need to work off of a large amount of data sets the way you would when using deep learning. So I think it really just depends on what you're trying to achieve. Abhishek, do you want to add to that?
I already answered on the chat. So people are going for DL and ML, specifically ML algorithms, most because the situation is more favorable to ML compared to other techniques that we have in AI. It's very easy to get a lot of data, like take the example of social network and your browsing history based on just. So there was this case where Target find out that a lady is pregnant based on the items, the products she was buying, and they used this information to um, give ads to her that were related to all the items which are used during pregnancy, and they were giving her deals and everything. So this is called targeted marketing. And so because of the data, they were able to find out that, and that is why I think because we have so much of data, it's easier to use ML algorithm or ML techniques. It is easier to use ML techniques to achieve the goals, or impart intelligence in the systems.
Great. Thank you. Okay, so let's move on to the next slide. So kind of looking at historical trends in deep learning. So obviously, the idea of artificial intelligence, machine learning goes back, since the 1950s, and there have been what people call like these AI winters, right? Where we've kind of made progress in a certain area through the algorithms that were available, and people really thought it was going to take off, and it becomes this huge trend. So, for example, at one point, cybernetics, was considered the big thing in AI, and then that trend kind of died off, and then connectionism and neural networks became kind of a big thing around the 1980s. And people really thought that we were going to have robots everywhere, and and that trend kind of died off again as well. And then now we are starting to go through another kind of leap and trend in AI because of deep learning, because of the availability of the data that we have collected, and also that processing power through GPUs, which is great. But it is good to recognize that these concepts have been around for a long time. Neural networks have gone by other names for a long time, such as multi-layer perceptrons. And now, most recently, we have more data available to train on, obviously, especially with things like YouTube and just even cell phones. Companies are collecting data on our everyday lives every second. So having that availability and able to, do things like marketing to us as individuals has gotten easier. And then, of course, computer infrastructure has improved through hardware and software. So the models that are available for us to gain information on have grown exponentially. And then the applications, have gotten better over time, and the solutions that we're able to, used to solve real world problems, you know, they're able to do that over more complicated ways, and they're more accurate now than they used to be. So yeah, in this way, like, artificial intelligence really has a real world impact that's increasing. It's going to be applied to really every industry. I think a lot of people are starting to realize that, and that's why a lot more people are getting on board and wanting to learn, you know, what this really means and how they can get involved in deep learning. Did you guys want to add anything to that as well?
No, we can go next.
Okay.
Yeah, wait.
Yeah, go ahead.
So,
Yeah.
like, there have been AI winters, right? So, like, deep learning is like breaking that AI winter and bringing us closer to our goal to like to really model how humans like understand the world and like live in it. So, like, if you like see the trend that's going on right now, the research that's like big companies like Google, Facebook, Microsoft that are like rigorously trying to like do research in it, build products in it. If you see this, if you like want to follow this trend, I'd say like this is the best time for like jumping on to this bandwagon, if you say.
Yes, I would agree. Okay, great. So let's move on. They cover obviously a little bit more on like a broad level overview of what all is going to be covered in the book in the next section. But I don't think we need to do that on here because you can read it yourself. And of course, they go more in depth on all of the ethics and kind of the history of AI and deep learning and machine learning. But you know, again, we kind of expect you to read the book as well. So hopefully, this has at least given you side. So to start to get into the meat of what we're learning here, if you're going to do AI, machine learning, and deep learning, you have to have a background in mathematics. And if you're like me and it's been in college, you know, you just have to take time to review all that information and kind of work out that muscle again, so that you can actually help perform these computations and have an understanding of what the machine is doing behind the curtain, as they say. So kind of the basic building blocks of linear algebra, which is essential to deep learning, are just understanding the vocabulary. You know, what is a scalar? What is a vector? What is a matrix? You know, what are tensors? You know, I didn't know what a tensor was when I started learning about this stuff, so it was really good once I was able to find that out. So yeah, so it's pretty straightforward once you break it down. You know, a scalar is just a single number. A vector is an array of numbers arranged in order. A matrix is a 2D array of numbers, and tensors are an array with 3 or more matrices. And these are all identified in different ways. So for example, normally when you write a scalar, it's written in italics, and it's usually lowercase variable name, right? A vector, usually when you write it, it's given in bold typeface, also usually a lowercase name. And I have, of course, included examples. So a vector is on the upper right-hand side, and a 2D matrix is on the lower left-hand side of this slide deck, for those of you that are following along. And then a matrix is usually represented by a bold typeface A, uppercase A, of course. And then one thing that we didn't include in here that they did talk a little bit about were sets. When you need to index a set of numbers of a specific vector, you would write it in a set. So for example, with engineering, you might think of this just also as an array. So you would do s is equal to, and then those specific indexes. So let's say, for example, 1, 3, and 6. And then if you want a vector containing all the elements of a specific array or vector, except for what's located within those indexes that set, you would just do, that lowercase a, and then with a subscript of minus s. So they give that example directly in the book, but I just figured I would touch on it even though it's not here on the slide. So yeah, these are just the basic building blocks when you're looking at the calculations to do linear algebra. And then having a better understanding of how to identify these matrices when they're written out in these calculations, it can kind of look like a foreign language if you're not used to it. So first, you would know through this representation that this matrix A has a height of m and a width of n, right? So it's just a pretty basic representation. And that is with a bold typeface A. The bottom right entry is represented as a non-bold, so a standard typeface A with an M and an N. So you know that that represents the one all the way at the bottom right. And then if you see something like a bold typeface A with an I and a colon, that denotes the horizontal cross-section of A with the vertical coordinate of I, or also known as the ith row of A. And then the last example that was given here is this f of A with a subscript of I and j. This gives the elements ij of the matrix computed by applying the function f to A. So it allows you to index matrix x value expressions that are not just a single letter. So it's just another way to represent that expression of that value. Did you guys want to add anything to that when identifying these matrices?
Is everyone clear with the just checking on
the chat thread? Yeah.
Okay, I guess people don't have questions, so we can go.
Okay, perfect. So a big topic when you start getting into working with matrices is the idea of transposing matrices. So a transpose of a matrix is just a mirror image of the matrix across a diagonal line. This is also referred to as the main diagonal. So this is the example given here. The picture on the upper left is just how you would represent the transpose written out in a mathematical form. And then the bottom right is how you would actually see that written out fully. So this doesn't just apply to matrices, of course. Vectors can be thought of as matrices that contain only one column. So a transpose of a vector is a matrix with just one row, right? And then a scalar can be thought of as a matrix with just a single entry. So a transpose of a scalar is just itself. So I think that's pretty straightforward, unless anyone has any questions on that or comments. No? Okay, we'll move on. So when you start working with matrices, we just want to make sure that you understand the basics, just like you do with regular mathematics. So when we add matrices together, they have to have, well, if they have the same shape, so when we add matrices together, if they have the same shape, you can add by their corresponding elements. So for the example given in the book was C is equal to A plus B. So that's, you have one matrix A, and you're going to add it to matrix B, and that's going to produce matrix C, where C of I of j is equal to A ij plus B ij. So what that's saying in this case is we're just adding each part of the matrices together. So as you see here, x1 gets added to y1, which will give you your third value in your third matrix of C. And you can also add a scalar to a matrix or multiply a matrix by a scalar by performing that operation of each element of a matrix. So as shown here, for scalar multiplication, you would just multiply the A by each section. So that's pretty straightforward as well. If you wanted to represent that written out, you could also do, so di of j is equal to a times bij plus c. But anyway, that's all located in the book. Yeah. And something that is unique to deep learning is that it allows for the addition of matrices and a vector yielding another matrix. So this is also known as broadcasting, where you have implicit copying of B to many locations. So for the example that's given here, if you have this matrix, it's a 3x2 matrix on the top left, and you want to add that other vector, right, which is just a 1x2, you would broadcast those values in that vector, and then you can perform the calculation. I think that's pretty clear, unless you guys want to add anything to it.
Yeah, keep going.
Okay, cool. Yeah, so from there you can start thinking about multiplication of matrices and vectors. So here, you know, obviously if you have matrix A, it must have the same numbers of columns as B has rows, right? So in this example, you have n columns in A, and that aligns with n rows in B, right? So if A is the shape of you know, m by n, and B is the shape of n by p, then C is the shape of m by p. So and that's written out as well mathematically at the top right. And this is not an element-wise product. This is what's called a dot product between two vectors. So when you get your final calculation for C, you know that C is going to be p columns wide by m rows high. Yeah. So, and again, I think that's pretty straightforward as well, unless you guys want to add anything to it.
Yeah. Can you explain a bit more about the difference between dot product and a cross product?
Yeah, so from my understanding, the cross product or the element-wise product, that's a matrix containing a product of the individual elements. So in that way, it wouldn't, so the dot product, I wonder, I should have included a different image. And there's no way to like write it out on here. Abhishek, do you have a good way to explain that?
I think you're right, but whatever you have covered so far, and the image is also fine. Just that we have to keep in mind when we are doing the matrix multiplication is that so here A has dimensions m cross n, and B has n cross p. So if you see the one of the dimension is same in both the matrices, only then you can multiply them. And the element in the element wise product, you multiply element with the element. So in the element matrix, in the element wise multiplication, you will multiply a value with all the elements. And in the cross product, you would do a matrix multiplication, which Laura just explained.
Right, so in the element-wise, would it then have a sum of all of them, or am I confused by that?
I'm not sure if you can do element-wise with two matrices.
Okay.
It's only, you can do it with scalar value.
Okay, that makes sense to me. How about you, Faison?
Yeah, I understand.
Okay, cool. So these are just some matrix product properties that you should be aware of. So matrix products are distributive, which is shown here. So you can take A and multiply it by each element within the B plus C matrix. So then you have A times B plus A times C. It's also associative. So A times BC is equal to BC, or I'm sorry, AB times C. It is not commutative, so you have to be aware of that. So the product of A times B is not necessarily always equal to the product of B times A. And the transpose of a matrix product has a simple form, as shown. Let's see. I think that's all the notes I had on that one. Yeah. And I think that's pretty straightforward. The book also gives a few more examples as well. And this, basically, getting to know all these building blocks allows you to create a system of linear equations, right? So you can start identifying what's actually happening here. So we already went through kind of what these things are, but when you're looking at AX is equal to B, you have identified your known matrix, you have identified your known vector, and then you have the vector you're trying to solve for, which contains the unknown variables. So you can rewrite it as follows, where you're taking every element within matrix A, and you're multiplying that by X, and then you're adding that throughout until, and that'll make up your known vector, which is B. And then you continue to do this all the way through, and it can also be written out in long form, but the matrix vector product notation provides a more compact representation for equations of this form, right? So it just allows you to get a better understanding in shorthand form of what's happening as well. Did you guys want to add anything to that?
No. So I hope everyone is clear with the representation. It's basically all these system of linear equations can also be represented in the matrix format. Yeah. Also, I would like to get back to the element-wise multiplication.
Are you there? Yep, go ahead. Did you want me to go back a slide?
Sorry, yeah, so we can do the element-wise matrix multiplication only if the dimensions of both the matrices is same. So in that case, we'll just multiply all this, we multiply both the matrices element by element. So for example, if we have A and B, assuming both are 3 cross 3 dimension, then we'll multiply A11 with B11 and A12 with B12. Yeah, so we just do 1-to-1 multiplication or element by element multiplication in both the matrices.
That makes sense to me. Were there any questions in the chat about it?
No.
No? Okay, cool. So the next topic that was covered is the identity matrix. And so this is a matrix that does not change any vector when we multiply that vector by the matrix, right? And in this case, I of n is representative of basically the numbers of elements that make up the main diagonal, right? And the main diagonal is obviously that diagonal down the middle, and everything else is just zeros. And so this is needed to understand so that you can start doing the inverse as well, which is on the next slide. Because when you start taking the inverse of matrices, let's see. Yeah, so utilizing that identity matrix will allow you to do the inverse in this way. And I got this picture from a site called mathisfun.org, which is really cool. And basically the way it walks you through it is that you start with your matrix A next to your identity matrix I. Of course, you add row 2 to row 1, and then you divide row 1 by row 5, and then take 2 times the first row and subtract it from the second row, as shown there. Multiply the second row by -1/2, swap the second row and the third row, subtract the third row from the second row, and then you're done. So in this way, matrix A has been made into the identity matrix, and at the same time, the identity matrix has been made into the inverse of A, right? When you see it all written out. Did you guys want to add anything to this portion before we move on?
I would just say that to find the inverse, like if you do it manually, then it's a pretty tedious process. So we have libraries which actually gives us APIs that we can use to find the inverse of the matrix. Yeah, but just
Awesome.
it's good to know how do we do it mathematically.
Definitely. Did you want to add anything, Faison?
No, go ahead.
Okay, cool. So the next topic that's covered is linear dependence and span. So we know that the span of a set of vectors is the set of all the points obtainable by linear combinations of the original vectors, right? So for the inverse of A to exist, there must be exactly one solution for every value of B. So it's also possible to have no solutions or infinitely many solutions for some values of B. However, it is not possible to have more than one, but less than infinitely many solutions for a particular value of B. Does that make sense, or do you think we need to go more in depth?
Yeah, it makes sense. Just there was a question in chat like, can you put some light on how these things are related to deep learning in a practical manner? So I would like to answer that.
Yeah.
Like these things are important for like understanding deep learning, right? So like if you have a like good grasp of basics, a good grasp of like linear algebra, the probability theory, and these things, if you get to understand this better, then you would understand how the deep learning model works in real life, and if there's a problem, if there's a issue when running a deep learning model, then you can like go to the like open the box and try to understand where it goes wrong and like correct it, like see your code and like try to like debug it. This is important when you're trying to go a bit deeper, right? So you have to have a bit like better understanding of linear algebra and this sort of things. That's what I'd like to add.
Thank you. I think that's a good answer. Yeah, and I think over time also, just based on other lecture series that we've covered in the meetup groups, when you start getting into more theoretical problems, there are many layers of abstraction. And if you can't kind of visualize what they're talking about when looking at the mathematical calculations, you'll have a hard time understanding what the machine's actually doing, right? So at least for me, going through the mathematics and getting a better understanding of what all these things means has allowed me to have a better conceptual understanding of that abstraction. What do you think, Abhishek?
Yeah, you are right. So there is one way where we can just use the API that a library is giving us and implement the algorithm. But if you want to fine tune it or improve the performance, then you need to understand the mathematics of the algorithm, how it is working, and what can we fine tune, and how does changing one parameter affects the other. So if we do not, and to understand all those things, it's important that we understand the basic linear algebra or the calculus being used there. So yeah, all this is part of it. All this can be considered as building the foundation on which you can build your machine learning or deep learning understanding concepts.
Thank you. Thank you. Okay, great. So the next topic that was covered is linear dependence versus linear independence. And so for a pretty straightforward definition of these two, so linear dependence, if one vector in the set can be defined as a linear combination of the others. So in this case, as you see on the right-hand side, we have vector v and x, and then the vector w here of the other two. If no vectors can be written this way, then the vector is said to be linearly independent. So you can't take two of these and put them together to get the third, right? I think that's pretty straightforward as well. So the next section starts talking about norms. And a norm is a function that assigns a strictly positive length or size to each vector in a vector space, except for the zero vector. So that's shown in this depiction here on the left-hand side. And it starts going into what a Euclidean space is. And so here, elements in this vector space are usually drawn as arrows in a two-dimensional Cartesian coordinate system, starting from the origin of 0, 0. And then the Euclidean norms assigns to each vector the length of its arrows. So when you boil it down, this is also just known as the magnitude. Yeah. And then for the Frobenius norm, in this case, this comes just from the inner product on the space of all matrices. So you want to just take the multiplication of the inner product of, all the matrices located within that Cartesian coordinate. And I'll be honest, at this point, I started to get a little fuzzy on how to fully talk about all this stuff, but I'm hoping my co-hosts will help me out here a little bit. Do you guys have kind of a simplistic way to describe these norms that you can share with our audience?
I just keep the formula in mind and
Yeah.
to get an intuition of it, it's basically if you see the second example B where the vector size is on the x-axis, the x value is 2 and the y value is 2, and the hypotenuse or the norm, it's finding the length of the hypotenuse of the right angle triangle made by the y and the x values. So it's under root of x square plus y square. I just have that intuition, but it's only helpful to me, I guess. I'm not sure. Yeah. As we keep going, eventually, I guess you will start developing that intuition. Yeah, that's my hope. But I'm not a mathematics teacher. I'm sorry.
No, that's perfect. Thanks, Abhishek. How about you, Faison? Did you want to add anything to that?
Yeah, so like understanding the norm, like it's like, as you said, measuring the size of a vector, right? So take an example, like in a machine learning problem, when you have like a multidimensional data and you want to like get the best like line or a plane or something that would divide the data and like get the best optimized like classifier, then you have to have uh, like a differentiator, a error uh, kind of thing. Like you have to find the distances between those points, and you have to find the best like line which would like classify in between these, right? So like if you want to measure these uh, distances, like you have to use these norms, right? So like the given example is of like this, uh, taking the like squares of the distances between the points and like taking the square root, like it's called the Manhattan distance, I think, right? So like you have to like find the best error rate which would differentiate in between these.
Thank you, Faison. That's awesome.
Yeah, one more thing I'd like to add, like one of my members of the group,
Mm-hmm.
he tried to like write code for this Frobenius norm, right?
Mm-hmm.
So the difficulty he faced was so he was using like a cross product instead of a dot product in this, right? So the Frobenius norm uses dot product for like finding the distances, right? So you have to like know the difference that here we use dot product instead of a cross product.
Thank you. I'm sure that'll be really helpful. Okay, great. So let's move on. Yeah, so the book also gave some examples of special matrices of diagonal matrices, of course, that just have values down the main diagonal and rest is zeros. Symmetric matrices, there's an example on the bottom right, where they have the same values on each side of the diagonal, but not down the diagonal. And then orthonormal, or I think there was another way to say that as well, orthogonal or something, matrices. And then these are the rules to look for when you're trying to identify an orthonormal matrix. The inverse of an orthogonal matrix is orthogonal, of course. A product of the orthogonal matrix is orthogonal, and if A is orthogonal, then I'm not really sure what that DET stands for. Do you guys know?
It is the determinant.
Oh,
Yeah,
determinant. Oh, awesome.
I did.
Cool. We're going to cover that later. So the determinant of A is equal to 1, or the determinant of A is equal to -1. Cool. So yeah, so just some other things to look for when you're identifying these matrices. So then they go a little bit into eigen decomposition. And in this case, the matrix is represented in terms of eigenvalues and eigenvectors. And factorization of a matrix, this allows you to do factorization of a matrix into the canonical form. And so here depicting what it looks like before you do the multiplication, and then after the multiplication, that it's almost doubled in size in a way. Anyway, would you guys say that's doubled in size after the multiplication? No, it's probably more than that. Oh, it's squared. Duh.
Yeah.
Okay. Yeah. So again, at this point in the book, my understanding became a little bit fuzzy, but you're unlikely to get into these higher level mathematics until you really start getting your hands dirty with deep learning. So just start getting yourself comfortable with them, and then what it means when the time comes. Abhishek, do you have a good understanding of how to do eigen decomposition?
Yeah, he went to sleep.
Oh, okay. Well, that's okay. We can also include more resources on each of these sections. I think it would be helpful to post videos of how to do these as well later on. And then I found this really neat GIF of singular value decomposition that I wanted to share with the group. So again, my understanding of how to perform the mathematics for this is fuzzy, but this just gives you a visual representation, which is helpful. Faison, did you want to add anything to that section?
No, go ahead.
No? Okay, cool. And then the Moore-Penrose pseudo-inverse. I know that this obviously has something to do with projections of part of one matrix to another. But this was really complicated and kind of above my understanding at this point. But I just wanted to include the visualizations in the slide so that everyone has something to refer back to when they go from there. And again, I don't mind finding additional resources and videos. I'm going to do it for myself anyway, so I'm going to go ahead and post those in the future for people to refer back to. And they also cover the trace operator in this case, and the determinant, as they talked about earlier. And of course, here we have an example of the specific formula for the determinant. And they show here that if we have a 3×3 matrix A and we want the specific formula for its determinant of A, then this is the value that you'll get. But I'll post additional resources to help everyone understand how to actually perform these calculations. And then they actually go through another example in the book more in depth, but I'll leave that up to you, to review yourself as well. Additional resources that can be found, the first two were referenced in the book, the Matrix Cookbook and Shilov's Linear Algebra book from like the 1960s or 70s. But more recent resources that you can also reference would be Khan Academy's Linear Algebra and Udacity's Linear Algebra Refresher. These give more modern approaches, and they're also really fun and interactive. So I would say, use those, have fun with it, take the time to learn this stuff. It is definitely a requirement if you're going to get into deep learning and machine learning. And how are we doing on time? Oh, well, we're actually over time anyway, which is fine. So were there any other last-minute questions in the chat that we should answer before saying goodbye to our friends?
Yeah, one question was that what are the properties of a determinant?
Ooh, properties of a determinant. Let's see if I have that in my notes here. So I don't have it in my notes, but I would be happy to post that online. I'm going to make a note to myself right now so I can add that to the list of additional resources to send out to people. Were there any other questions that we didn't cover?
This is off topic, but still, is there a way to do these weekly instead of bi-weekly?
I would be fine with that. I personally would not be able to lead the Google Hangout session every weekend, but I know, Faison, you also offered to lead these sessions. If you're available, we can discuss the logistics further. Or if there's anyone else out there that's willing to be kind of a co-organizer or co-host on these sessions that would be willing to lead them on those off weeks, I'm happy to coordinate with them as well. Just send me a message on the meetup page. Yeah, and we can go from there. And again, as a reminder, please, we're asking for volunteers to do a presentation like this. As I said in the original email, it can be as short, as 10 minutes, as long as an hour, as long as you try to cover as much material from the book as possible to give people an understanding of what was covered. Ideally, people will read the book on their own and try to gain as much knowledge from it. And then the goal of these Hangout sessions is really to come together and share our knowledge as a community. So we're hoping that people will volunteer and sign up on that Excel spreadsheet to do that. Yeah, were there any other questions?
No, it's okay.
Okay, perfect. Well, we want to thank everyone for joining us today. I think this was a good first intro to deep learning and the linear algebra needed to start on your journey in doing deep learning. Yeah, they did say in the book they expect people to have some, background in mathematics and computer science and engineering. I don't think that's necessarily true. I think if you're focused and determined to learning this material and willing to get up to speed on your own, then anyone should really join and jump in and start learning about this stuff and having fun with neural networks and machine learning. So I want to thank my co-hosts, Abhishek and Faizan, for joining us. And yeah, and we'll go from there.
Yeah, thanks for presenting.
Okay. Thanks, guys. And we'll see you next time.